Okay, so one of the keys here is understanding how an ammeter and a voltmeter affect your circuit. The ammeter, in order to measure current properly, it has to be hooked up like this, right? In series, in the line you're trying to measure the current. And it has a very, very small resistance. In fact, typically we say it's an ideal ammeter, which means it has zero resistance and it doesn't affect the circuit at all. But in actuality, anytime you reach into a system to take a measurement, you're changing the system in some way, and so your measurement is a little tiny bit different than it would be if you hadn't reached in there to take that measurement. But we try to make it that change as small as possible. So an ammeter has a very small resistance. Ideal ammeter, zero resistance. And voltmeter, you have to hook it up in parallel to measure the voltage on something. So you don't want the current to all of a sudden go through the meter instead of through what you're trying to measure the voltage of. So it has a very high resistance. An ideal voltmeter has infinite resistance. So we'll assume these meters are ideal. So if S1 is open, and what's the resistance here? Infinite. Right? A voltmeter has infinite resistance, an ideal voltmeter. So can any current get through here? No. This is basically an open circuit. So nothing goes through this resistor. We could just take this whole thing out of our drawing. It's not doing anything. No current is going through that. It's an open circuit at that point. So all the current is going to go around the outside. If S2 is open, all the current goes through here. And then it comes up and around the outside here. So this is just like 4 resistors in series. You see that? So this has an equivalent resistance with both S1 and S2 open. Those are resistors. 4 in series. So this is the same as was it 2, 4, 6, 8 ohms? And what is this? I said 10? So what do we get for the current? Okay. What is that, 1.25? And where was that voltmeter? So one end of the voltmeter, I'm going to get my colored pen out again. One end of the voltmeter is hooked up to this voltage. Normally when we get to a resistor, the voltage changes. But what's the current through that resistor? 0. V equals IR for a resistor, so it has no voltage change across it. Whatever the voltage is on the right side is going to be the same as the voltage on the left side because there's no current through it. So this is all the same voltage right here. And the other end is hooked up at a different, it's all the same voltage here, right? So we have to figure out what those are. What should we call this 0 right here? If that's 0, then this must be plus 10. I'll use green for plus 10. So the green is plus 10. We've dropped by 4 ohms to get to the purple. 4 ohms times whatever 1.25 is 5 volts, right? So that means the purple is 5 volts less than 10, which is 5 volts. You agree with that? I'm just walking through the circuit. I start out at 0. I go up through the battery. I'm 10 volts higher now. And then I go through 4 ohms of resistance. And 1.25 amps times 4 ohms gets me 5 volts lower than what I was on this side. So that means I'm now at 5 volts. And 1.25 times 2, it's 2.5, right? So I'm 2.5 volts lower than I was at the purple side when I get to the blue side. So this here has to be 2.5 volts. And then I go through another 2 ohm. I drop by 2.5 volts again. That gets me to 0. This is 0 volts here. So what two sides is my voltmeter? My voltmeter is hooked up between 2.5 volts and 5 volts. So it's going to read 2.5 with the right side being higher than the left side. All right, let's see what we get. The two switches are open. 1.25 amps through our ammeter, 2.5 volts with the right side being higher potential than the left side. If we switch those, then we would get a negative 2.5, right? It measures the red one with respect to the black lead. Okay?
How's there voltage is not current? I just understood.
Question, how do we get a voltage there when there's no current through that branch? Because the voltage is sort of always there. It's like pressure in a pipe with water, right? Even if the water is not flowing through that branch, it could have pressure in it. So if you open the switch, water would flow through that branch, right? So that's what it's telling us here. There's a potential there. There's a potential difference across that switch, which means if we close the switch, current would flow. Which direction would current flow? From the high potential side. Current, remember, is these dots are electrons moving. Current flows the other direction. This is showing the electron movement in the wires. These are the negative charges. Current is the opposite direction. Current flows from high potential to low potential. So it would go from the right side of that switch to the left side. The right side is at higher potential. So if the current was flowing, it would come along here, up here. Part would go through the upper resistor. Part would go through that switch if we closed it. Matt?
Can you go through how you got 2.5 volts again?
Yeah, I picked a starting point. So my starting point was here. I called that 0 volts. That's the bottom, the low voltage side of my battery. Then I went up through the battery. So now I'm at plus 10 volts. Right? Like elevation, right? I went up a flight of stairs. Now I'm 10 steps higher. So all along this path, right? Conductive paths are equipotential surfaces. This entire green line is 10 volts. Now I hit a resistor, and when I go through a resistor, the voltage changes by the current times the resistance, right? V equals IR for a resistor. So I dropped, and I just did it all in one step here rather than do 2 steps, but I went through 4 ohms going from the green to the purple. 4 ohms multiplied by my current, which is 1.25 amps, gives me 5 volts drop. So I was at 10. 10 minus 5 is 5. So now I'm at 5. So nothing can change me here. This is just a perfect conductor. Right up to here, right up to here. It's all 5 volts. Then I went through this resistor. 1.25 amps times 2 ohms gives me 2.5 volt drop. I was at 5. 5 minus 2.5 is 2.5. So now I'm at 2.5. And then I said, well, if this is 2.5, then this is also 2.5 right up to this resistor. And because there's no current through that resistor, there's no voltage drop, right? V equals IR. If I is 0, V is 0 for the resistor. So there's no voltage drop. So if the left side is at 2.5 volts, the right side has to be at 2.5 volts. So part of my voltmeter is hooked up to 2.5 volts, part is hooked up to 5 volts, so it's reading a difference of 2.5 volts. Okay? Did you go beyond that? What happens if we close switch 2? So when we close switch 2, what does the circuit look like? It looks like this. Is that right? Because we've shorted out. Where's our? When you close switch 2, you create a zero resistance path around those resistors. Remember, if there's a zero resistance path, all the current takes the path of zero resistance. So that's what we call a short. So we've shorted out those two resistors. We've basically removed them from the circuit because we created the zero resistance path around them. But we still have those other two. And S1 is open, so nothing's getting through that 2 ohm resistor there next to the switch 1. So our circuit looks like this. So we have half the resistance we had before, so we have twice the current. Okay? So what is my voltmeter going to read? Where's the voltmeter hooked up, basically? It's basically hooked up one side over here, and the other side over here. Is that right? So if we call this 0 volts right there, then this is going to be 10 volts. And then we drop by 5. 10 minus 5 is 5. And then we drop by 5 again, we get back to 0. Good. So the voltmeter is hooked up between 10 and 5, so it's going to read 5 volts.